welcome to the last real full class of the summer session. The final exam is going to be held during the next class period, which is on Wednesday. So that will be held at the regular class time. The format will be similar to the midterm. So it will be open book, open notes, and I expect you'll have a lot of time to work it. Let's say I'm not designing the exam for what normally they're about 2.5 hours during the regular semester. You'll have all that time to work it, but I don't expect it to be much longer than your midterm. That is 3 or 4 questions with subparts hitting the key points. So I wouldn't be stressed about time on that, but I would definitely put in the time to study, because it's better to work things out early if you have questions, and just to grasp the understanding of the topics that will be on the exam instead of doing it real time. The final exam in general is cumulative, but I am going to emphasize first order circuits through motors. So what that means is you still have to know the early material. You still have to understand Kirchhoff's laws and Ohm's law and power and node voltages. But those are actually they are topics that are included in the later material. So in general, it's cumulative, but definitely study first order circuits through motors, and we're going to cover motors today. So in addition to motors today, we're gonna start out with that. I'm going to do a final exam review, and that will concentrate again on first order circuits through the last material of the semester. So my office hours will be held right after class, so you're welcome to join that to ask questions or just listen to questions from other people. And definitely ask questions during this class by chatting or unmuting yourself, but otherwise please stay muted to keep the background noise low. And as always, if I drop off during the class for technical issues, wait around a few minutes and I'll do my best to get back. Knock on wood, hasn't happened yet. Okay, so you should be able to see the roadmap slide now. So we've covered all of the circuits topics and all of the electronics topics, semiconductors and op amps. And we just finished up the digital logic and systems and microcontroller topics. So, and I'll give you a flavor of the types of questions I would ask you about microcontrollers during the review today. I'm really looking for you to just have an overview knowledge of microcontrollers and to be able to work some basic logic problems. For example, if I connect a logic gate to an output of a microcontroller to the logic port output of a microcontroller, then to be able to work some logic problems. And I'll show you what that is when we get to the review. I'll show you types of problems like that. So now we're on to motors and servos, and I'm going to do a survey, an overview of motors and servos. We're going to cover DC motors and stepper motors and servo motors. So we'll jump right into that. There are these other two topics I show, sensors and applications. We're actually not going to dig into those during this class. There are slides up on Canvas if you're interested in those topics. Basically, the sensors topic is a photodiode, connecting a photodiode to an op-amp circuit to show applications of light sensing and an application of an op-amp circuit. And for applications, there are actually slides on voltage regulators. So you can take a look at that if you're interested. Those topics will not be on the final exam. They generally are for your interest and for future use if you're interested in those. So take a look at those if you're interested. Okay, so let's start into motors. Let me bring those slides up. Okay. So on your screen, full screen, you should see a slide that says DC motors. If you don't, let me know. What I like to start with is just some general definitions, general terms that we will use when talking about motors. So this is a cartoon, I like to call it, out of a book that shows the major parts of a motor. So the stator is the part that stays still. It contains, well, the case of the motor and usually some coils or magnets. There's a rotor, that's the part of the motor that spins, and it spins on a shaft, and that shaft rotates on bearings on either end of the stator. So I'll use the words stator and motor and shaft when talking about the parts of a motor in general at a high level. Let's do this. Let's set the foundation for how you cause a force to happen with current flow, and just do a basic overview. You might remember this from physics. So if I have a setup like this, where I have some kind of voltage source and maybe a resistor and maybe a switch. And so imagine this, and then I have these two rails. So these rails conduct, and then you have a sliding bar perpendicular to those rails. So imagine this bar can slide left and right. It'll stay perpendicular to those rails, but it can slide left and right, maybe roll left or right. And it's also conducting. So current, when the switch is closed, current can actually travel through that resistor, through that switch, down through the sliding bar to the other rail, and back to the source. I also have, shown by these X's, these are indicating a magnetic field into the screen as you're looking at it. So imagine a magnetic field created by either a permanent magnet or an electromagnet outside of these rails. So these rails and this bar are sitting in that field, which is oriented perpendicularly to the plane of the page right now. Well, if I have a current flow, if I close the switch and have a current flow through that bar, I will actually get a force induced on that bar. F equals, the force vector equals IL cross B. Okay, so if you remember your cross vectors, or your cross products of vectors, I times L is actually the current magnitude times a length vector, and the length vector is pointing in the same way of positive current flow, positive charge flow through this bar. So the vector would start up at the top here if I have a positive current flow IA, and then point downward. And B is the magnetic field into the page. And if I take the cross product IL cross B, you can imagine doing the right hand rule. IL cross B would have a force to the right as you see it. So causing a current to flow and through this bar in the presence of a magnetic field will cause this sliding bar to have a force on it, and it will move to the right. If you want to move the bar to the left, well, reverse the current flow. Have IA a negative value, which essentially has positive charge flow upward through that bar, and you'll get the force in the opposite direction when you take the cross product. So this is called a linear DC machine, or a linear machine, and it explains the fundamental force induced on that conductor, that bar, under this condition. There are only a few examples of linear machines that I can think of. One of probably the most dramatic that I've seen, you can get on YouTube and see this, is the linear machine called the naval railgun. So again, go on YouTube, Google naval railgun, and you'll see this this DC machine that causes a projectile to launch at hypersonic velocities out of that barrel. So there aren't too many examples. This is, again, a sort of a dramatic example. It's kind of neat to watch on video, but it is an example of IL cross B directly induced. There's a lot of current that is caused to flow through a carrier and in a strong magnetic field, and that causes a force and acceleration of a carrier, which has a projectile on it. So again, if you want to see an example of a direct linear machine, not a rotational machine, you can take a look at that. There is the more common example of implementation of IL cross B to cause something to move is a DC motor or rotational motor. And so this is a diagram of basically how that works. So imagine this. Imagine down here at the lower left, there's some voltage source or some current source, and these wires connect to brushes. So these kind of blocks on either side of this round object are brushes. They conduct current from the brush to this round object called a commutator. So that commutator is split down the middle so that it's insulated, so that current cannot flow from one side to the other of that commutator. But current can flow from the brush to the commutator, and that commutator can spin, and the brushes rub along against that commutator. Well, let's suppose the coil is oriented as shown. So current would flow up through the brush into the commutator half here, which is connected to this single coil of wire, and current would flow along, as the red arrows show, along this coil back to the other half of the commutator, to the brush, back down the wire. Okay, if you follow that current path and you acknowledge that there's a magnetic field here, there are two magnets, two permanent magnets, it looks like in this case. So north pole on one side, a south pole on the other side of the coil, causing this magnetic field from lower right to upper left in this diagram. And with the current flowing from lower left to upper right, if you do the right-hand rule and calculate IL cross B, then you would see there's a force up on the upper left side of this coil and a force down, because current's going in the opposite direction with the same magnetic field direction, force going down on the lower right side of this coil. That would cause a rotational force on this coil, and it would spin. So if you follow this round, if this coil spins 180 degrees, then you have the same force applied up on the left, down on the right, and this coil wants to spin. This is really conceptual because, well, what happens when this commutator spins 90 degrees? You're sort of shorting between those brushes. That might cause a problem. So let me show you a more realistic example of a motor, and that would be, well, this diagram here. So this shaft and rotor of a motor shows commutator bars on the left and brushes, and the commutator has more than 2 bars. It has probably about 8 here, 8 bars. So the brushes can never touch common bars in between them, so there's never a short between the brushes. So imagine this, imagine each one of these commutator bars is connected to a coil of wire. So maybe right here there's a coil connected or a wire connected, and it wraps through the slots in the rotor and might wrap around there a few times so that you get a few coils of wire on each armature slot there. And that happens for each one of these, each pair of commutator bars. So now the brushes can conduct current through the coils of wire. And so that's really more accurate of how a motor is represented. The magnetic field could be caused by permanent magnets on either side of this rotor. And sometimes the magnetic field is actually induced by coils of wire external to these coils. They're separate from these coils here. Okay, so take a look at this setup here. In this setup, the let's see, so you still have the rotor. You're looking kind of down the shaft of the rotor here. You can see the coils indicated by those circles around the perimeter of the rotor, and current would be going into where the X's are shown from your perspective and out of where the dots are shown. So you'd have current flowing that way. You can also see current flowing into these, well, field windings. So here's a winding that kind of goes into the top. So coil of wire would wind into the top and out of the bottom here, causing a north pole on the left of what would be an electromagnet. And then on the left side of the screen, you have current going in the top, out the bottom. Again, a coil of wire set up around this kind of arm sticking out of the stator, and that would cause a south pole as viewed by the rotor in the middle. So you could actually create a the magnetic field using current instead of permanent magnets. And so this motor would, again, IL cross B on each one of these legs, these coils of wires here, would cause the motor to spin. So there are many different kinds of motors. There are AC motors, there are DC motors, there are brushless motors, there are stepper motors, there are different kinds of motors. Here is an example of, here are examples of 4 types of motors. And what we're going to look at are 2 of these. Okay, so here's the common DC motor. This is the kind of motor you'd have in a lab kit or buy at the local electronics store off of DigiKey, where you just want to apply DC and the motor spins. So this is a common permanent magnet DC motor. And if you look, so I have this graph here of torque on the vertical axis and speed, think RPM, on the horizontal axis. And so this would be the type of characteristic you would get, torque versus speed, for a common DC motor. So you could think of the motor as you apply a load to the shaft. You might you would increase the torque required to keep the shaft spinning. And so there's a characteristic, in this case it's linear. So if you actually don't load the motor at all, just let the shaft spin, that's as fast as the motor is going to turn. That's this lower right intercept right here. And then as you load the motor with torque, then you would see the speed reduce. So the motor would slow down, and there's actually a point called the stall torque, where the motor doesn't spin. It has 0 RPM, and you have high torque and 0 speed. So that would be the characteristic of a common DC motor. We're going to look at a different kind of motor, which is a synchronous motor up here in the upper right. And there are different types of synchronous motors, but we're going to take a look at a stepper motor. These 2 motors are common, so that's why I teach these. You're likely to run into these in future projects. So this stepper motor, if you look at this characteristic, it's a straight up and down line, which means under normal operation, this motor spins at 1 speed within the normal operating range of torque. So there's a specification for torque range of this motor, and if you operate within that torque range, the motor will spin at a speed that you designate, and I'll show you how that works. So this is another way to operate a motor, another type of motor. Okay, and so something to note here, the speed is independent of load of the torque, and in the lower left, the DC motor speed changes with load, with torque. Okay, so let's dig into the common DC motor. Let's talk about speed control and direction control of a DC motor, and then we'll do the same thing for a stepper motor. So looking at DC motor speed control, so you can operate a DC motor by just connecting a voltage source to a motor. You apply a voltage, DC voltage, across the motor, and it spins. If you want to vary the motor speed, a common way to do that is called pulse width modulation. So modulation means you're changing some characteristic of a signal, right? You've heard of amplitude modulation, frequency modulation, maybe phase modulation. In this case, you are modulating or changing the pulse width of a voltage applied to that motor. And so what you do is you pulse the motor with varying pulse widths to control the average power delivered to the DC motor. And so you're going to essentially turn the power supply on and off at a very fast rate, and vary the on time versus the off time. And that's usually characterized with what's called a duty cycle. So you might have heard the term duty cycle before. It's a fancy term for what's the percentage of time the power is on versus the cycle period, versus this is a periodic waveform, it's a periodic square wave. So what's the time on versus the total period? Okay, I'll show you examples now. If you, for example, just connect a motor to a 5-volt source, it's a 5-volt motor rated for 5 volts, you connect it to a source, and you just leave the voltage on, that would be a 100% duty cycle. The voltage is on 100% of the time. And so that would be the fastest you could spin this 5-volt motor. Okay. If you want to slow that motor down, what we're going to do is reduce that duty cycle from 100%, well, to something lower. So here's an example of an 80% duty cycle. So if you look, this waveform has a period, right? It's periodic, and it maxes out at 5 volts, and the min down here is at 0 volts. And so you're just turning on and off this voltage source. And it's high, the voltage is high 80% of the time. Okay, so 80% of, really 80% of all time average, or 80% of one cycle, the voltage is high. So that's where this duty cycle comes from down here. What this does is this has the effect of applying an average voltage to the motor. So again, you have a certain amount of current through the motor, you have a certain voltage applied across the motor on average, and so that would be the average power delivered to the motor. So since for a given load, you would be slowing the motor down. If you wanted to slow the motor down further, here's a 20% duty cycle depicted. So the power supply is essentially on only 20% of the time. So the average voltage is, well, 20% of 5 volts. Okay, so that would slow the motor down. Notice that it's pulse width modulation, so you have the same frequency, but different pulse widths, and that's how you control the motor speed. And the frequencies that are used for this are typically in the kilohertz range, maybe depends on the motor, but a couple kilohertz up to tens of kilohertz. And so why do this? Why not just change the voltage? Well, it's really easy with a microcontroller. Remember, we talked about microcontrollers can output digital logic levels on or off, right? High or low, 5 volts or 0 volts. And then you can connect those ports, as I showed last time, to a transistor or another equivalent chip that can turn on and off higher current loads, right? You might only have a couple milliamps capability out of your microcontroller, but you connect to a transistor or a different type of chip, I'll show you. And now you can pulse higher amounts of current. So it's really easy to pulse current on and off. It's harder and more complex and usually less efficient to adjust voltages in a kind of a continuous range in between on and off. So you use different pulse widths, the same frequency, and that causes an average voltage to change. You can hear this in some, for example, some electric drills, some rechargeable drills, battery operated drills. If you pull the trigger just a little bit before the motor starts making noise, so turn the drill slowly, you can sort of hear this, you can hear this really high frequency whine. And so you can actually hear the pulses that are being produced to turn that motor. So that's pulse width modulation. If you want to stop the motor, we would call that a 0% duty cycle. And so 0% of the time, the voltage is high. So that would stop the motor. Okay, so that is directional control. I'm sorry, that's speed control of a motor, of a DC motor. Let's talk about directional control. So now you can control the speed. Let's suppose you want the motor to go in reverse. You can use what's called an H-bridge, and there are different embodiments of H-bridges, but this is kind of the classic schematic that you look at to talk about an H-bridge. Kind of looks like an H, right? You can see the legs of the H, the crossbar of the H. Imagine you have a motor and 4 switches, and up top there's a node voltage, 5 volts. Maybe it's a 5-volt motor. And at the bottom, we have a ground. So there's some, you can imagine a voltage source connected between the top and the bottom node here. So current is trying to flow with a positive 5-volt source. Current would want to flow somehow from 5 volts down to ground. And we're going to control the current flow with these 4 switches. So let's do this. Let's define current going left to right through this motor, right? From left to right through this motor would be the forward direction. That's kind of arbitrary, but let's define that as the forward direction. Let's define current going right to left as the reverse direction of the motor. So if you take a motor, you connect it to a 5-volt power supply directly, it'll spin a certain direction. If you reverse the terminals, just swap the terminals on the motor, it'll turn the opposite direction. So that's what we're trying to do. We're trying to cause the motor to spin opposite directions by changing the direction of current flow through this motor. So if you want current to flow left to right, you could close switch A and close switch D. So you'd have this. Current would flow down through switch A, left to right through the motor, and we'd call that the forward direction. And so we can make a table of this. Let's suppose here are the states of the switches, and here's the direction of the motor. Let's suppose we want to reverse the direction of the motor. So now I want current flowing from right to left through that motor. So all you have to do is, well, open up switch A, open up switch D, close switch C, close switch B, and current would flow from right to left through that motor. So here's the switch state versus motor direction, and that's how you would control the direction of the motor. Okay, so you change the switch states in order to change the direction. And now you can think of combining this also with pulse width modulation. So instead of having a 5-volt DC source up here, you could think of maybe having a pulsing DC source up at the top, pulse width modulated, and that would cause the motor not only to have control and direction with the circuit, but you could also control speed. Okay, so what I want to show you now is how you would do this with transistors. So this, I show mechanical switches here. You could do that, but let's suppose you want to control direction of a motor with a microcontroller or some other digital circuit. So I'm going to stop the share now, and I'm going to start up my whiteboard here. Okay, so at this point, you should see my whiteboard. You should see a schematic on it that says H-bridge with transistors, and you should be able to see that full screen on your end. If you can't, let me know. So this circuit should look a lot like, well, the H-bridge we just looked at. There are 4 transistors instead of 4 switches, and what we would like is to be able to control current direction through this motor. So I've defined forward, left to right, reverse, right to left. So I have 2 transistors that should look familiar. At the bottom, right, this is an NPN transistor, so that if you apply a voltage to this lower left node B, and suppose these resistors are designed such that when you apply a logic voltage at each one of these logic variables, that the transistor saturates. So if I want current to flow through this lower left transistor, I apply, let's say it's a 5-volt logic circuit. I apply 5 volts at B, at node B, and that transistor conducts, turns on. It's like a closed switch. Same thing with D over here. This is an NPN transistor, NPN bipolar transistor, and it, you apply a voltage to D, it saturates, that transistor current flows. If you apply 0 volts to D, the transistor is in cutoff, and no current flows through that transistor. Okay, let's look at the top transistors now. So here, this is what's called a PNP transistor on both sides here. And you'll notice the difference is that the emitter, which is on the top in this case, has an arrow pointing into the transistor instead of out of the transistor. Kind of a mnemonic to remember that is NPN has the arrow not pointing in. PNP is the opposite. Okay, PNP transistors are just like NPN transistors, except reverse the voltage polarities and reverse the currents. So instead of IC, right, the collectors on the lower left, or on this, so on this transistor I'm pointing at, the collectors on the bottom here, instead of IC flowing into the collector, IC actually flows out of the collector. And the emitter current actually flows into the emitter instead of out of the emitter. And base current flows out of the base instead of into the base. And so that's really the big difference between NPN and PNP. So in order to control current, the collector current with this PNP transistor the way it's shown here, if you want to cause current to flow through the transistor, you have to cause base current to flow, right? And to cause base current to flow from emitter to base, you would actually have to do this. If you have 5 volts node voltage at the emitter, and you want current to flow from emitter to base, remember, instead of base to emitter, emitter to base, if you want current to flow this way, you'd actually have to ground or apply 0 volts to A, right? When you have 5 volts at the emitter and 0 volts at A, you would have current flowing from the emitter to the base through the base resistor to A. Okay, it's just the opposite of what we saw with the NPN transistor. You still have this base emitter junction modeled as a diode. It's just flipped around in polarity, right? So so that's what we have to pay attention to here. To make current flow through the NPN transistor at the bottom here, you apply 5 volts at B. To make current flow at the PNP transistor, as shown here, you'd have to apply 0 volts at A so that you cause current to flow. If you apply 5 volts at A, you have 5 volts at this node, you have 5 volts at this node, you have a diode with the same node voltage on both sides. So there's no voltage across the diode. So that would cause the current to stop flowing. Okay, so let's do a truth table here. So if I want current to flow in the forward direction, I want current flowing down through that transistor and down through that transistor, okay? And so that means to turn transistor A on, let's call this transistor A, or to saturate it, I would actually have to apply, let's do this in the same color, I would actually have to apply a logic 0 to A to cause collector current and base current to flow. And then to turn D on to cause current to flow, I would actually have to apply a logic level 1 to D to cause base current to flow. To turn off B, I would apply 0, right? NPN transistor, 0 volts here, 0 volts here, no current flows. And then to turn off C, I would have to apply 5 volts or a logic level 1 so that no base current and no collector current flows. So that's how you would cause these transistors to make this motor. That's how you would set these transistors and the logic levels to make this motor spin in the forward direction as shown. So let's spin the motor in the reverse direction now. I want current flowing through transistor C and transistor B. And really all I have to do is reverse these states. So A would be shut off, which is a 1, right? C would be on, which is a 0. B would be on, which is a 1. D would be off, which is a 0, okay? So it makes sense. You just reverse the states of the transistor and it should do the opposite thing. So this would be appropriate for connecting these 4 logic inputs to 4 pins or 4 ports on a microcontroller. And then you can control the direction of a motor with, let's say, an Arduino. You could also control the speed of the motor by turning these ones, or let's say, instead of having a constant 1 and 1 for this A and B signal in the reverse direction, you might pulse width modulate those. And that would cause that motor to not only spin in the proper direction that you want, but also you could control the speed. Okay? So I just wanted to show you this. You should just kind of know the general concepts. I introduced PNP transistors. We're not really gonna work with that. You should know how to work with NPN transistors, and you should be able to know that, right? A of 0 turns A on because that causes current to flow through the base and then through the collector of that PNP transistor. Okay. And again, if you have any questions, shoot me a chat or go ahead and break mute and we'll talk more. So what I'd like to do now is expand on this a little bit. So if you have a project where you need to control a motor, there are some specialized integrated circuits out there that do this for you. So I'm going to touch on this briefly. You might look at some circuits like this. You should see a slide right now that says H-bridge with an integrated circuit. And this is actually an H-bridge chip that has this inside. So if you look at the diagram in the upper right of this slide, I'm showing two triangles that I indicated were called buffers when we were talking about logic circuits. I think it was one of the clicker questions. And that just means that a logical high applied to the input is a logical high on the output. It essentially allows higher current to be driven either into or out of the output with a low current input. So here's the motor, and you could see that if you have a high on one side of the motor and a low on the other side of the motor, it'll spin. If you reverse those senses, then the motor will spin in an opposite direction, and that's indicated down here in the truth table. And these diodes are curious. I want to point this out because if in the future you ever control DC motors with a microcontroller and electronics, don't forget these diodes. Your circuit may work for a little bit and then stop working all of a sudden. Because of this, the motor has inductance. It is made with coils of wire, and those coils of wire have inductance. And we saw that when you try to shut off current very quickly, in other words, a big DIDT through a coil, you get a large voltage. Sometimes that voltage is large enough, tens, hundreds, thousands of volts, where you can actually burn out the chips that are connected to your motor. That's what these diodes do. They protect your motor by discharging. They cause a dissipation element in order to take the energy that was stored in the inductors and put that energy somewhere, dissipate it somewhere. It's kind of funny, you look at these diodes, let's say VCC2 is 5 volts and this motor voltage is 5 volts. It looks like these diodes don't do anything because when this motor voltage is 5 volts, you actually have a reverse biased diode at the bottom here, so no current flows. And if VCC2 is 5 volts and the motor voltage is 5 volts, you don't have any current through that diode either. If you make the motor voltage on the left 0 volts, again, you don't have any voltage across the diode at the bottom, so it's not conducting. And you have a reverse bias diode at the top, so it's not conducting. It looks like these diodes never conduct. Well, they do. When you try to shut off the motor, you will get either a big positive voltage. You could get either a big positive voltage at this left node, which would cause current flow and power dissipation through this diode, right, from a big voltage to 5 volts VCC2, or you could have a big negative voltage spike at the left side of this motor here, which would cause current flow up from ground to that negative voltage. That power, that energy stored in the coils would be dissipated in the diodes, which can handle that power. They're designed to handle that power, and they won't let the voltage rise above a certain level, about the forward voltage of the diode. So just pointing that out, if you ever have problems with controlling a motor electronically, don't forget your diodes. That may be the cause. That's what I just showed you is the DC motor overview. You saw how they were made. You saw how to control the direction and how to control the speed of DC motors. They are low cost. Typically, there are low cost versions. They have their applications. and you can control speed and direction, but not very precisely. There are ways to use feedback loops, but generally, if you're trying to control speed of a motor or angle of the shaft of a motor very precisely, or if you connect the motor to, let's say, a belt or a chain, if you're trying to control linear motion very precisely, that's where a stepper motor comes in. So you should see a slide right now that says stepper motors. Let's talk about precision control with a stepper motor. You can control speed with a stepper motor. You can control rotor angle very precisely with a stepper motor. And then if you have a gear, a belt, a chain, you can control linear position very precisely. So applications are things like print heads on printers, where you need to displace the print head from a certain position, very precise distance. If you're trying to point an antenna, let's say, from a rover on another planet, you need very precise control. So you might use a stepper motor to control the angle of something either directly or indirectly through gears. If you've used 3D printers, you've probably used something with a stepper motor, because again, obviously you need, or maybe not obviously, you need a precision control, X and Y control, and Z control of the head of the 3D printer, and also CNC machines. So some CNC machines use stepper motor. Here's the stepper motor on the left side of this machine, and here's one down here, controlling, and one up top, controlling the 3 axes of this CNC machine. And so that's where stepper motors shine. That's where they are good to use. Let's talk about the principle of operation. How do these stepper motors work? And this will also show you why you need to include a little more complex control for stepper motors. So imagine this. I'll show you this kind of static, this diagram, and then I'll show you an animation of this. So imagine you have a stator, so it stays still on the outside, and on the inside you have a rotor. And so that rotor can spin about this center dot. Let's insert some coils of wire that aren't shown here, but imagine you have a coil of wire wrapped around this A tab or pole, you can call it either, and then the wire kind of comes around back and continues and causes creates an electromagnet coil of wire around this A prime. So if you create a north pole at A, as seen by the rotor, you create a south pole at A prime. And you can energize, you can cause that magnetic field to turn on and off by applying current through those coils. Okay, now let's imagine the same setup around B and B prime. You have a coil of wire, B and B prime. You can energize that coil, that pole, that phase separately. And the same thing for C and C prime and D prime. Okay, so now let's imagine a circuit that can energize those coils, that can cause current to flow. So here is a DC source and a 4-position switch, and if you change the position of the switch, that causes coils A, B, C, or D to be energized, to have current flowing through them. Okay, let's suppose the stator and the rotor are in the positions shown on the left. If you energize stator, let's call it tab A and A prime here, what that will do is this rotor will want to stay in that position. Okay, the rotor wants to rotate to minimize what's called the reluctance of this, essentially a magnetic circuit of the system. So if I energize A, the rotor wants to minimize the gap between A and 1 and A prime and 4. If I then de-energize A, I just move the switch over here, and then I energize B and B prime, what's going to happen is this rotor wants to close the gap. It wants to minimize the reluctance of the system, so that 2 will align with B and 5 will align with B prime. So the rotor is going to turn 1 step to the right. Now imagine the rotor in that position. Again, this is a static explanation. 3 is somewhere around here. If you energize C, de-energize B, energize C, tab 3 is going to turn to align to C, and 6 will align with C prime, so the rotor turns one more step. Okay, we're going, obviously you're not going to, well, not obviously, you might want to not do this with a switch. You might want to do this with transistors. I'll show you how to control these phases, these coils with transistors instead of the switch. Let's take a look at this, at an animation of this. So here's, you should be able to see sort of a spinning rotor and the lit up coils that are energized. So the rotor turns every time a coil is energized or a pair of coils are energized. The rotor turns one step. It's kind of jumpy in here. The animation shows these kind of discrete steps in between, but really one step is where you go from a coil being energized, the rotor turns to align with that coil, the coil is then de-energized, the adjacent coil is energized, and the motor turns one step. Okay, so that's what it looks like. So is there a standard amount of tabs present on this most stepper motor stators? You know, it's pretty common to have on the small stepper motors 4 phases. And so you'll see the small ones that you use in lab projects, you'll have 4 phases to control. There are different kinds of stepper motors. There are actually stepper motors with teeth on them where you can get a very fine resolution where you're not really aligning coils with tabs on the rotor. You're actually aligning teeth. There's sort of these teeth around the where the outside coils are, and you can get very fine motion. So I would say standard small motors, 4 phases, and I'll actually show you that on a few motors in a minute. Okay, so here it is. Here's a motor. This is a small stepper motor blown up. Up on the right, you have a diagram showing the 4 coils, and this schematic diagram shows how you would connect this motor to transistors in order to control the motor with, let's say, a microcontroller. So in this case, we have a 5-volt common that's applied to this motor. So that 5 volts, so there's no connection at the yellow, there's no connection at the brown, they're just crossing wires. There is a connection from the 5 volts to this red wire and to the green wire. So common among these phases is 5 volts. Then the other side, the other 4 nodes connected to these coils are connected to this set of transistors. So Q1, Q2, Q3, Q4. So if you saturate these transistors, you will have current flow to ground, right, from the 5-volt common through the coil to ground. So now you can control each one of those coils electronically with something like a microcontroller. So down at the bottom right, you'll see the step number and the corresponding states of those transistors. So to hold this motor at step 1, Q1 is saturated, Q2 is in cutoff, Q3 is saturated, Q4 is in cutoff. So if you want to move the motor 1 step, then you would de-energize the state shown in step 1 and control the transistors as shown in step 2 for this row, and so on. So then you could turn 1 more step by energizing the phases according to step 3, and likewise for step 4. If you want the motor to keep spinning, you go back to 1. After 4, you go back to 1, and the motor will keep spinning in that direction. So to have a counterclockwise rotation, you would energize in this order: 1, 2, 3, 4, 1, 2, 3, 4. To have a clockwise rotation for this motor, you would just energize in the opposite order. So 4, 3, 2, 1, 4, 3, 2, 1. That would cause the motor to spin in the opposite direction. So that's direction control of a stepper motor. To control the speed, you just control the timing between steps. So you could use a timing, the timing peripheral of a microcontroller to determine how much time you want between each one of these steps, which has a certain step angle. Each motor will have a certain step angle defined for it. You'll see that in the data sheet. And I have an example in an upcoming slide. Okay, so you can control direction and speed with 4 digital inputs in just how you energize the coils. So you have actually 6 wires that interface to this motor. So it's not as simple as just applying a voltage to a stepper motor. You have to have some control in order to energize those phases. And so you might use something like a microcontroller or otherwise other motor controller to control the position and the speed by energizing the right coils. Okay, let's take a look at a different stepper motor. Here's another one. There's a schematic in the upper left that shows the 4 phases and the different signals you would apply. So this table on the right shows how you spin the motor clockwise or counterclockwise. You apply the positive voltage. This was probably a 5-volt motor. You apply the positive voltage all the time to the red wires, and then yellow, orange, brown, and black wires you energize, or I should say you connect to ground through a transistor or otherwise based on the table shown here. And so in the lower left, this is just another chip that you could use, and I showed this in a microcontroller example in a slide in the microcontroller set of slides. This is that same chip where you control with an open collector output the connection to ground or not at these outputs. So you could connect 4 of these outputs to the 4 wires of the microcontroller, black through yellow, and then the input could be connected to an Arduino or microcontroller, and you control the motor. Okay, so you can use different technologies in order to control high amounts of current through these motors. Transistor arrays, H-bridge ICs, or other motor drivers can be used. So finally, let's take a look at a motor. This is another motor that specified its coil resistance. So here's 90 ohms coil resistance. It's a 5-volt motor, so you're going to be drawing about 55 milliamps per coil. This motor had 20 steps per revolution, so 18 degrees per full step. So you could calculate how many degrees per second or revolutions per second or revolutions per minute based on that step size and the timing that you define to control the motor. So again, stepper motors typically require more current per phase than a microcontroller could provide. And if you try to connect a stepper motor directly to a microcontroller or anything else with digital only ports, then it might work, it might not, you might get unpredictable results with that. Okay, so that's kind of that's the overview of stepper motors. If you have a project in the future that needs precise speed or angle control or linear displacement control, a stepper motor would be a good choice. So there are some applications where you might want sort of a hybrid in between a stepper motor and a DC motor. You might not need the precise control of a stepper motor. You might want more like smoother motion in between position changes compared to a stepper motor, but maybe a DC motor alone wouldn't fulfill your needs. So that's where servo motors come in. Servo motors are motors, and they're a little more than a motor. They're kind of a whole control system that you would use on something like a radio control airplane, or some maybe a valve where you have to control the position of a valve based on a sensor. So they're usually used to precisely control linear or angular motion. An example is an RC car, right? You might want to control the steering on an RC car, or maybe it's some kind of self-driving car or drone. You could use a servo for that. This is the servo right here. You can see the arm out of the servo, so it would rotate about this Phillips head screw here, and in this case, it's controlling steering. In the lower right, this is an RC airplane, and you can see the servos controlling the elevator and the rudder connected by control rods. So you know, those are small, low power applications, but there are some high torque industrial applications too, where you might have some kind of robotic arm that needs control in position, and you could use servo motors for that also. So let's dig into this servo motor unit a bit and show what's inside. So here's a small servo motor. This would be one like on an RC car or an RC plane or a small drone. This is what's inside here. So a servo, let's kind of broaden out a bit. A servo mechanism uses feedback to achieve some desired result, like position or speed. So the servo part implies this feedback, this feedback approach. You have a desired position, you have a current position. They don't match, so bring them closer together. If the difference is big, that's a large error. Let's reduce that error. The servo motor typically controls position of a shaft, and you usually set the desired position of the shaft using some kind of control signal. And then there's some feedback, and it's the same type of feedback we talked about for op amps. It's a negative feedback that minimizes the difference between the actual position of the shaft and the commanded position of the shaft. That reduces the error between the two to 0. Just like in op amps, we reduce the input differential voltage to 0 through a feedback loop. Here, we're reducing the error to 0 between an actual position and a commanded position. Okay, so here's how it works. If you look at the diagram on the right, you have a motor controller. That motor controller applies power to this DC motor. So this DC motor is inside this servo motor, like this blue box around the outside is the motor. It's what's inside here. So it has a little DC motor inside. You know that we can control direction using some kind of H-bridge. So we can spin that shaft of that motor in either direction. That motor is usually geared down. So there's a gearbox here. So many turns of the DC motor shaft would be one turn of the output shaft. And so that there's a set of gears here. The output shaft is connected to a potentiometer. And so the potentiometer is actually used as a position sensor. So think about it. We showed that you can control a voltage between two limits using a potentiometer, right? So you turn the knob between one extreme and the other of a potentiometer, and you get a changing voltage. Well, you could map the voltage to the angle of the potentiometer. So that's really a position sensor. So the output voltage of the potentiometer would tell you the position of its shaft. So that's what's done here. So that voltage out of the potentiometer is used by the motor controller for knowledge of the actual shaft position. So there's a control signal coming in, that's the controlled position. There's an actual position, that's the shaft position here. And the motor controller's job is to apply voltage, positive or negative, to this DC motor in order to control the motor, to turn it, to minimize the error between the commanded position and the shaft position. Let's break this motor apart a little bit. Let's look inside. And I stole this one from SparkFun. You could read a lot about these types of stepper motors there. And here are the parts. So the motor controller is on this small circuit board here. You could see the wires connected from the motor controller to the motor, and from the 3 wires from the potentiometer to the motor controller board. Here's the DC motor, right? There are 2 terminals on that DC motor. You could spin either direction by applying a positive or negative voltage there. And you could also control the speed using pulse width modulation if you wanted. And then here's the gearbox up top. You can see it's geared down to connect to that shaft. The shaft has an arm on it, so these holes are meant to go into some kind of control arm that extends off of that that arm. And then the potentiometer is right here at the bottom. This is the bottom of the potentiometer with its 3 terminals, A, W, and B. Those connect back into the microcontroller. So there's this loop from the controller, through the motor, through the shaft, back to the potentiometer, back to the motor controller. Okay, so you can see all those parts right here. If you get to the point you have the opportunity to use one of these in a future project, you can use it like this. So it's common for these smaller servo motors to be controlled with pulse width. It's sort of like pulse width modulation, but a little different. The pulse doesn't control speed. It actually controls position. So as I vary the pulse width, that maps to an angular position of this servo. So the typical rotational range of these small servo motors is 90 degrees or 180 degrees. And you're going to use pulse widths to control that angle. The period is typically 20 milliseconds of these pulses. And the range of pulse widths is 1 to 2 milliseconds. So you use a microcontroller to control the position of the servo motor shaft, and you're going to vary. You're going to have a frequency of 50 hertz or a period of 20 milliseconds, and then you're going to control the pulse width between 1 and 2 milliseconds to control the angle. So if this is a 90-degree servo, 1 millisecond pulse would correspond to moving the position to maybe 0 degrees. And then 2 milliseconds would change the shaft to 90 degrees. So you vary between 0 and 90 by varying the pulse width between 1 millisecond and 2 milliseconds. Okay, so straightforward to do if you can use a microcontroller, and especially if you read about using the timer peripherals on a microcontroller to control the pulse width. Okay, so let me give you some key points, kind of key takeaways comparing these motors that we talked about. So servo motors are used to control, or they use a control signal and negative feedback to position a motor shaft. If you compare these motors to DC motors, well, a DC motor is actually used inside of a servo motor, but there's negative feedback inside of a servo motor. And you're actually using a pulsed voltage to control the position of a servo motor. You use pulse width modulation for a DC motor, but it's used for a different reason. You control the speed of a DC motor using pulse width modulation. If you compare servo motors to stepper motors, servo motors have a shaft angle that's controlled by this kind of closed loop system with negative feedback. You command a certain position, and there's a circuit inside the servo motor that minimizes the error between the commanded position and the actual position. Stepper motors, well, they are controlled in a completely different way. The shaft angle is controlled by energizing phases of the coils within the motor. So you need something like a microcontroller to control digital ports to control a stepper motor. And then you're using timing peripherals for a servo motor in order to control position. So just they have similar functions. All of these have similar functions. Turn a shaft or linearly displace something. They're controlled in different ways. Okay. So that's an overview of motors. What I would expect you to know for an exam is kind of these high-level facts. Generally, how a DC motor is controlled, direction and speed. Generally, how a stepper motor is controlled by energizing different phases. And generally, how a servo motor is controlled using a control signal and negative feedback. Okay. I think this is a foundation such that if you want to go use these in a project in the future, right, you have a foundation where you know, oh, okay, I know I can just spin a DC motor, or if I need position control, I could use a stepper motor or a servo motor. So this is kind of a foundation for that. Okay. All right. So this wraps up what I want to talk about on motors. And so what I'd like to do next is take a break, and then we're going to start review for the final exam. And we're going to start with first order circuits and then roll through the rest of the material, and I'll show some slides and probably, yeah, I've got some whiteboard work too, and we'll review. So let's do this. Let's take a break now. My clock says 5:06. Let's round up to 5:07. And so at 5:17, let's all meet back on Zoom. I'll leave the session up and go on mute. And so stretch your legs, grab a drink of water, and I'll see you back here at 5:17. Let's talk about the final exam. Let's jump into the final exam review. So covered on the final exam are a few topics. So we're going to start off with first order circuits, and then phasors and impedance. And so I'm kind of listing the general topics off of the schedule. If you look at the schedule, it has a list of topics lecture by lecture. And so we'll do first order circuits, phasors and impedance, operational amplifiers, and right before operational amplifiers, actually, transistors and diodes, semiconductors, digital electronics, or digital systems, and electric motors. Okay, so what I'd like to do, and again, if you have any questions, just shout them out, or shoot a chat. And well, I'm going to start off with first order circuits and then just work some problems. So if you have any specific problems, definitely let me know. Okay, so let me do this. Let's do a first order circuits problem. So this was an example from a prior exam. There are other example problems. There are 3 sets of problems on Canvas. You can take a look at those. Those are old exam problems. You can also take a look at the practice problems on linked to Canvas, and you'll see those practice problems have a little more explanation behind them rather than just the solutions. So you can take a look at those on Canvas. So let's work a basic first order circuits problem. Let me draw a circuit with a capacitor and a few resistors. So let's suppose we have a 36 volt source, and that 36 volt source is connected to a few resistors like this. It's going to have a switch in it. So the switch is actually going to open up at t equals 0. And a few more resistors, a couple more resistors. And of course, a reactive component, we need a capacitor. So this capacitor is going to have a value of 100 microfarads. We're going to have a resistor at the bottom, 5K ohms. This will be 10K ohms. The next resistor on that leg, and this will be 3K ohms. And so this is the circuit. We need the switch will open at t equals 0. And let's suppose that the switch has been closed for a long period of time. So before t equals 0, the switch was closed for a long period of time, and then all of a sudden at t equals 0, the switch opens up. Okay. Here is how I would recommend solving problems like this. I think, and I talked about this when we covered first order circuits, I think the initial and final value approach is usually easier, maybe less time consuming, as long as you can figure out the time constant. And so let's use the initial and final value approach here. So in this case, VC of t, let's find the capacitor voltage. Okay, so this is plus minus VC of t. So let's find that capacitor voltage. VC of t is equal to VF, the final value or the steady state value after the switch closes, and then plus VI, the initial value of the voltage. Oh, I'm sorry, the switch is opening. So VF is the final value after that switch has opened and you've waited a long period of time. VI is the initial value of the capacitor voltage right after that switch opens up, minus VF. So there's always an exponential in here, e to the minus t over tau. Tau is the time constant. Okay, let's figure out what the initial value is first. So let's find VI. Okay, so we can plug it into this relationship here. And so remember that the capacitor voltage, VC of t, current, IC of t, equals C dV dt. I know we're not finding current, but I want to show you this. It's important. This equation is important because the derivative of voltage has to be finite for a capacitor. You cannot have a discontinuity of voltage across a capacitor because then you would have an infinite derivative, and we don't have infinite voltage. We only have 36 volts. So voltage right before the switch opens up and right after the switch opens up is going to be the same, or at least it's going to be continuous. It's going to slowly change in a continuous fashion. The derivative is going to be finite. So let's look at the time period for t less than 0. Okay, because that's right before the switch opens up. We can draw out an equivalent schematic of this circuit at steady state before the switch opens up, right? Because it's been closed for a long period of time. So that circuit would look like this. I would have 36 volts, right? Connected through a 3K ohm resistor, a closed switch, right? T less than 0, closed switch, and then a 10K ohm resistor, and finally down at the bottom, a 5K ohm resistor, right? And the capacitor in the steady state looks like an open. It does not conduct current. So this would be VC of t here. And we can do, so let's see, we have 3 series resistors, and that VC of t is actually the voltage across that 10K ohm resistor, right? VC of t is between the same 2 nodes that are connected to the 10K ohm resistor. So I can actually use voltage division, let's say VDiv, to calculate that VC of t. Okay, so using voltage division, I have the source voltage across the series set of resistors times, on top goes the resistance across which I'm trying to find the voltage, and then on the bottom is the sum. I'm just writing K for 1,000 here, is the sum of all the series resistances, so plus 5K, right? And so that equals 20 volts. Okay, so that is the voltage across the capacitor right before the switch opens up, but because the derivative of voltage has to be continuous, we're also going to call that the voltage right after the switch opens up. So that's our initial voltage, VI, for the capacitor. Okay, so now we have VI. Now next we need to find VF. So let's find VF. So to find VF, we're going to go to the time long after the switch has been opened. We're going to find the steady state value. So for t much greater than 0, that means more than 5 time constants. We can redraw the circuit for T much greater than 0. So I have 36 volts. I have still these other resistors here, 3K ohms. And now I have an open switch, right? I have an open switch there. I guess I can draw in this 10K ohm resistor. Doesn't do anything because it's only connected on one side. You can get rid of a resistor that's connected only on one side, just it doesn't do anything in the circuit, so I don't have to draw that. And then I have 5K ohms. All right, and then I have a capacitor in steady state, which is also an open. And so this is my VC of t here for t much greater than 0. Okay, so that's what I want to find. That will be my final value of V. Well, notice that I have no current flowing through either of these, any of these resistors, really. This is 0 amps, right? So there's no current flowing through this resistor. That's 0 amps. That's 0 amps. So Ohm's law says this is 0 volts across that resistor. This is 0 volts across that resistor. If I do run a KVL equation, I'd find that minus 36 plus VC of t equals 0. So VC of t equals 36 volts. Okay, so that's my VF value. Okay, and so now I need to find the time constant. So time constant for an RC circuit equals R times C, and that's when you have something that looks like this. Remember we said that to the left of the capacitor, there's a source, and the switch could be, the switch is closed at the time we're calculating the RC time constant. But what we want is this R and this C in this RC time constant calculation. So we somehow have to reduce this circuit, right, or this circuit when the switch is open long after, or right after t equals 0, and into its Thevenin equivalent, so we can figure out what that Thevenin resistance is in order to calculate RC. Okay, well, so the equivalent circuit would look like this. At the point after t equals 0, the 10K ohm resistor is not in the circuit anymore. The switch is open, and we have a capacitor. And if I draw kind of a couple terminals here, let me indicate those by X's. To the left of the capacitor is a circuit that of which we have to calculate the Thevenin equivalent. We really only need the Thevenin resistance. And so if you zero the source, right, if you zero the source, make that 0 volts, it's a short. And if we look at the equivalent resistance looking into the terminals to the left, we have a 3K ohm resistor in series with a 5K ohm resistor. So this resistance would be 3K ohms plus 5K ohms equals 8K ohms, right? And that's connected to a capacitor that is 100 microfarads. Okay. And so we can calculate our RC value, tau equals 8,000, that's our R, times 100 times 10 to the negative 6th. If I can squeeze that in there. Okay, this is separate here. So that's how you calculate tau. And now we can plug everything into this, this equation here. So VC of t equals VF. VF is 36 volts. Plus VI minus VF. VI is 20 volts. VI is 20. Minus VF, 36. E to the minus t over tau. So this tau winds up being 0.8 seconds when you multiply that out. So e to the minus t over 0.8. And so what you get is VC of t, if you simplify this a little bit, combine some terms. 36 minus 16 e to the minus 1.25 1 over 0.8 t volts. T greater than or equal to 0. So that's how I would suggest solving this. Let's see. There's a question. Why is there 0 current? Was that for this case? Right. So for this case, there's 0 current because there's really no connection between this top node and bottom node of that source. There's an open here, right? And there's an open here, and there's no place for the current to flow. Okay. So why didn't I include the 10 k ohm resistor when getting the equivalent? So the 10 k ohm resistor, if you, in fact, let me draw that out. Let me write that over here. I can delete this here. So I'm calculating the equivalent resistance of this. The source is at 0 volts, 3 k ohms, 10 k ohms. That's not connected to anything, right? The switch is open, and down here I have 5 k ohms. Okay, so I don't include the 10K. There's 2 ways you could do this. You could say the 10 k ohm resistor is only connected on one side. There's no current flowing through it. It doesn't affect the circuit. You could hand wave it like that. Or you could say, well, 10K is in series with infinity, right? And open is infinity ohms if you want to do it mathematically. And you have to limit as that resistance goes to infinity. But what you would find is that 10 k ohm resistor has no impact on the equivalent resistance. Another way of saying that is the current flowing, right? You have an ohm meter out here on the right. The current flowing into the circuit to calculate equivalent resistance, remember, is V over I, right? Equals REQ. The current flowing through the 3 ohm resistor is the same as the current going through the 5 k ohm resistor. There's no current going through the 10 k ohm. And so these resistances are in series because the same current flows through them. So you add the resistances to get the equivalent resistance. Okay. So that's how I'd recommend solving a problem like this, using the initial and final value method. And then, what could you ask? You could ask for the equation, find the equation. I could say, well, what's the value of the voltage at t equals 1 second? So you plug 1 second in for t, or what's the value at t equals 5 seconds? Plug in 5 seconds for t. Okay. All right. Any questions on this? Okay. All right. Well, I'll erase this. If you have any more questions, we can revisit this at office hours. Okay. Then let's continue on with a phasor example. Phasors and impedance. I'll just write a Z. So let's suppose I have a circuit that looks like this. Let me leave some space so I can write my source here. So this source, Vs of t, equals 20 cos 10 to the 4th t minus 30 degrees volts. That's the source. It's a voltage source. And let's suppose I have a 2 microfarad capacitor and an inductor that is 12 millihenries and a resistor that is 150 ohms. And let's find I1 of t, and let's find I2 of t. So these are time domain voltages that we want to find, and we have a sinusoidal source. Okay, so if I know a problem is a sinusoidal steady state problem, what I do is I convert the whole circuit, I redraw it as a phasor circuit, or a circuit with phasors and impedance. So instead of Vs of t, I'm going to have Vs phasor, right, Vs with an underline, and that's going to equal 20 at an angle, right, 20 at an angle of minus 30 degrees, right? It's the magnitude or the amplitude and the phase of that original sinusoid. So that's going to be a phasor source. And then I'm going to redraw all of my reactive components as impedances. I just said Z1, Z2, and Z3, call them whatever you want. And the values I'm trying to find are I1, in this case, I1 phasor, and then I2 phasor. Okay, so we have to fill in values for these impedances. So Z1, well, that's the impedance of a capacitor, and the impedance of a capacitor is minus J times 1 over omega C. And so omega is 10 to the 4th, C is 12 times 10 to the negative 3rd, right? And so you plug that in there, and you get minus J 50 ohms, okay? The capacitance is always going to have a negative impedance. And then Z2, so Z2 represents an inductor, so that's going to be J omega L. So you plug 10 to the 4th in for omega. L is 12 times 10 to the negative 3rd, and you get J 120. And then Z3, that's the impedance of a resistor that's just equal to R. So that's equal to 150 ohms real. Okay, so now it's just a circuits problem, like a DC problem, with complex values, with complex valued resistors and voltages. So if I want to find, let's say I1 first, let's work on I1. What I could do is I could combine the impedances to the right, Z1, Z2, and Z3, into a single equivalent impedance. So I'd have Vs phasor, right? And then a single ZEQ, that's a ZEQ. And then I1 phasor is the current into ZEQ. So ZEQ is the combination of those impedances. And so Z2 and Z3 are in parallel because they connect to the same two nodes. Once you combine Z2 and Z3 into one impedance, then Z1 is in series with that combination. So you could say ZEQ equals Z1 in series with Z2 in parallel with Z3. Okay, and so you would do that just like you do with resistors, except now it's complex values. So if you plug these values into there, you get 58.5 plus J 23.2. And I'll let you run through these calculations. You can use these as practice problems to actually punch this into your calculator. So now we have ZEQ, and then I1 equals Vs. Remember, V equals IZ over ZEQ. Okay, so you say 20 at an angle of negative 30 degrees divided by 58.5 plus J 23.2, and that gives you an answer. And that gives you 0.318 at an angle of minus 51.6. degrees over all units amps. And so now, let's see, I think I can fit it at the bottom here on the screen. So now I can say I1 of t, that should be visible. I1 of t equals 0.318 cos. It's always a cosine. Omega 10 to the fourth, same frequency as the source. T minus 51.6 degrees. Okay, amps. All right, so that's how you solve this problem. We'll work on I2, but convert from time domain to a phasor circuit with impedances and phasor values that you're trying to find and phasor sources, calculate impedances, and then just figure out, do I need to use series and parallel combinations or voltage division, whatever you need. Okay. So let's find I2. So let's find I2 here. So what I see is that I2 can be calculated using current division, right? Because we have I1, this is still I1 here, right? I1 coming through. I1 splits or divides into two impedances, Z2 and Z3. So I could use current division. I'll say I div. And I would say that I2 equals the current coming into the parallel set of impedances, so that's I1, right? And then times the ratio of 1 over the impedance through which you're trying to find the current. I'm trying to find the current through Z2, so Z2, over the sum of the reciprocals of all the parallel impedances. So that's Z1, Z3, plus 1 over Z2, right? So that's just current division. So again, you know, I1 is this value here as a phasor. That's I1 as a phasor. Plug that in here. 1 over Z2, 1 over Z3, 1 over Z2. You use these values here, and you would get 0.248 and an angle of minus 90.3 degrees. So I2 of t is that phasor converted to the time domain. So the peak value of the cosine is the magnitude of the phasor, 0.248 cos omega 10 to the fourth t minus 90.3 degrees amps. Okay, so again, just converting to phasors, using impedances, and then everything you did for DC circuits works here.
Quick question.
Yeah.
So when we're doing current division, do we only use the reciprocals of the impedances if we're in the phasor domain?
No, for resistors, you also use the reciprocals. Okay. There's a formula that shows up in some books that says this, that like, but it only works for two resistors or two impedances, because if you multiply top and bottom of this by Z2, Z3, you would see that you get ... I1 times Z3 over Z2 plus Z3. Okay, and so at that point you're saying, oh, I just use the impedance of the other impedance, not the impedance through which I'm trying to find the value. The problem is that only works for two impedances or two resistors. So I don't like that equation, because what folks do is they try to put another impedance here when they have three, and it doesn't work. So I always use the relationship that has the reciprocals of impedances or resistances for current division.
Okay, and just to double check, if we're doing voltage division in the phasor domain, we don't use the reciprocals, right?
That's right. Right.
Okay.
Just the same thing for resistors. You don't use the reciprocals for voltage division with resistors.
Okay, got it. Thank you.
You're welcome. Okay, other questions on this? Okay, well, let's move on to the next topic. Let's take a look at something with an op amp. So, share my screen here. Okay, so it says clicker up top, but we don't have clickers during remote teaching. So you should see a screen that says op amps, and it has an amplifier. So take 30 seconds and give this a shot. Try to figure out what is the value of V out. Okay, so this circuit should look familiar. It's one of the common circuits. So remember, there's that decision tree that says if you have negative feedback, it's either a common circuit or use a negative feedback approach. And if there's no negative feedback, it's a comparator. Well, this circuit has negative feedback because there is some connection between the output and the inverting input. Okay, so what I would recognize this as a non-inverting amplifier just by comparing the schematics of this with what we talked about in class. Or again, you could derive the output versus input using the negative feedback approach. So in this case, the gain would be 1 plus the feedback resistor over the resistor that goes to ground. That's a gain of 5. So we have 10 volts. Okay. So V in is 2 volts, V out is 10 volts. All right. And again, stop me if you want to spend any time on one of these. Here's another problem. Similar, take 30 seconds, and you should recognize this as a common circuit also. So if V in is 4 volts, what is V out? So this circuit is one of the common circuits. It is an inverting amplifier whose gain is the feedback resistor minus the feedback resistor divided by the series resistor that goes to the input voltage. So this would be 2K over 8K with a negative sign in front of it, and it would have a gain of 0.25. So if V in is 4 volts, V out would be 1 volt. Okay. All right, let's do another op amp problem. How about this one? You should still be, I'll give you a hint, you should still be able to do this one quickly. So take 30 seconds and try this. So at first the circuit might look, well, unfamiliar. But if you notice, I have, let's see, a resistor connected to the output. That's just a load resistor. I have a resistor between the inverting input and the output, that looks like a feedback resistor. And then I have a resistor going from the inverting input to ground. And that's, so sometimes you don't draw the common circuits exactly like we drew in class, just maybe it just doesn't fit well on the schematic, or you have to have the input on one side, on the opposite side compared to what we drew in class. So you could redraw the circuit like this. Right, the input's applied to the non-inverting input. There's a feedback resistor of 12K. There's a resistor from the inverting input to ground of 3K, and then a load resistor. So this is actually another non-inverting amplifier, and it has a gain of 1 plus the feedback resistor over the resistor to ground. So the gain would be 5. And let's see, we have, 5. Gain is 5. That's what we were looking for. Okay. Let's try an op-amp problem that is not a common circuit. So take a look at this one. So if you want to find the output voltage, this one you should be able to do pretty fast. Take a minute and try to solve this one. Okay. Well, let's talk this through first. We do have negative feedback. There's some connection between the output and the inverting input of the op-amp. So that means the input differential voltage is 0, and we have 0 current going into the inputs just by nature of the op-amp. So if I have a node voltage here of negative 10 volts, that also means I have at this upper left node a node voltage of negative 10 volts because there's 0 volts between those two inputs. Let's look at current. If I have 2 milliamps flowing down to ground here, that means that, I have no current going into or out of this input. So 2 milliamps must be flowing through that 4K ohm resistor. That means I have 8 volts across that resistor with the plus on the right. So I have 8 volts there. Let's see, I have a voltage here. I know that voltage. I actually know the voltage across the 2 milliamp source because I know the node voltage up top here at this node. That node voltage is negative 10. So I know the voltage across that, between that node and ground, which is the voltage across that source. And then let's see, I'm trying to find VO. So I think I have enough to find VO now. Let me write those in. So here's my negative 10 volts across the source because I know that node voltage. Here's the 8 volts across the resistor here, right? Oh, lost my screen. And then I have, so 8 volts there. And so I can write a KVL. Let's start here. Minus negative 10 minus 8 plus VO equals 0. Okay, so VO equals negative 2 volts. Okay, any questions on that? Okay. All right, let's go to another problem. As you can tell, there's probably going to be an op-amp problem on the exam. So definitely work an op-amp problem, understand how to work these. Okay, so what is V out here? So take a minute and try to figure this out. You know, kind of a couple hints. It does have negative feedback. You do know the voltage at this node because you have negative feedback. And I would say you could figure out the current through the 2K ohm resistor and the 1K ohm resistor to write a KVL. So take a minute and do that. So this takes maybe an extra step compared to the last problem. You do know the circuit has negative feedback, so there's 0 volts between the inputs. That means the node voltage here, right, at the non-inverting input is negative 6 volts, so that the node voltage at the inverting input is also negative 6 volts. So we know this voltage right here at this node, the node voltage. That means we know the voltage across this 2K ohm resistor, so we can figure out the current through that resistor. So we know this current through the resistor. We know the current from the current source. We know there's no current into or out of the input of the op-amp. So what's left? KCL will tell us the current going through the 1K ohm resistor here, and then that'll give us the voltage, and then we can write a KVL equation. So if I put those values in, this node voltage is 6 volts, negative 6 volts. That means we have negative 3 amps going down through the 2K ohm resistor. If you do a KCL at this node with 5 milliamps coming in, negative 3 milliamps coming out, or equivalently 3 milliamps going in, you get 8 milliamps through this 1K ohm resistor. Now you have that voltage. So now we can write a KVL equation, maybe right here. Let's see, minus negative 6, minus 0, plus 8, plus V out equals 0. And you get negative 14 volts. Okay. Let's do one more op-amp problem. Try this one. Notice that there's no connection from the output to the inverting input. That doesn't go through a ground or a power supply. So that should tell you something. So take a minute and determine what is V out. So my hint on this problem was there's no connection between the output and the inverting input through a component that doesn't go through a power supply or ground, and that means that there's no negative feedback. Okay, so no negative feedback, which means this is a comparator comparing the voltages at the op-amp inputs. So we need to figure out what this other input's node voltage is. So we have 10 volts applied across two 3K ohm resistors. There's zero current going into the op amp, which means the same current is going through each one of these resistors, so they are in series. I can use voltage division to figure out that this voltage is 5 volts, right? 10 volts across two 3K ohm resistors, I get 5 volts here. So I have V1 equals 4 volts, node voltage V2 is equal to 5 volts, V1 is less than V2, so V out is approximately VEE, which is connected to ground there. Okay? Questions on that?
Yes, I have a question.
Yeah.
So I caught on from your hint that this was a comparator, but it was kind of confusing seeing if something doesn't have negative feedback because I saw that the inverting input was connected to V out, but I see that 10-volt source is that how you tell or?
Yeah, so the connection cannot go through a node that is connected to a power supply or ground. And the reason is, negative feedback works because this output in some way can influence the inverting input. But in this case, this node up at the top is always held at 10 volts. So no matter what this output does, that node is held at 10 volts and will not affect the inverting input. So that's why. So when you identify negative feedback, the only way you have it is if there's some connection between the output and the inverting input that doesn't connect to, through that path through a power supply or ground.
Okay, thank you.
Okay, sure. This 1K ohm resistor, in fact, is the pull-up resistor that we talked about. This is assumed to be one of those comparator chips. It would work with an op amp, but this looks like, in this schematic, a comparator with an open collector output. So the comparator can actually pull the output to ground. It can do that, but it can't actually supply a voltage to the output. So that's what this 1K ohm resistor does. It's a pull-up resistor that pulls the output up to 10 volts unless the output is pulled to ground by that op amp. Okay. Let's try a more kind of qualitative problem. What does a bandpass filter do? We talked a little bit about filters. Which one of these? Take 15 seconds and answer that to yourself. So working on your lab, we talked about filters for the sinusoidal lab, and a bandpass filter passes the frequencies in the middle of a band. So low frequencies are blocked, high frequencies are blocked, some frequencies around a defined pass band are allowed to go through. So a bandpass filter blocks frequencies lower and higher than a pass band. All right. The comparator was actually a good transition into digital circuits because the output of a comparator is either high or low. So take a minute and convert this value to hexadecimal. So we talked about a way to convert binary values to hexadecimal values by looking at 4-bit words, starting at the radix and going either direction, both directions from the radix. So we're going to divide this binary number up into words of 4 bits or nibbles. So we're going to take the 0011 and then again adjacent groups of 4 bits. So this 0011 is a 3, right? This is a decimal 3, binary converted to decimal, and then you keep working to the left. So this 1110 is a hexadecimal E, okay? And then we're left with 2 bits, so we actually have to add leading zeros to this number. It doesn't change the value, but you get a hexadecimal 2. And then you can work to the right of the radix, and you get 10, and we have to add trailing zeros here. So I add my trailing zeros, and 1000, 1000 would be an 8 in hexadecimal. So you concatenate these together, keep the radix in its position, and you get 2E3.8. All right. Okay, let's see. Someone said, can I go back to the last example really fast? Is this the one that you wanted to see? Two before. That one. I want for that one. Let's see. How about this one? Okay. Do you have any questions on this, or do you just want to glance at it? Okay. I think there's some op-amp problems on the practice problems linked to Canvas. So take a look at that. There's a comparator example and some negative feedback examples. And then also there are examples posted, old exam problems as review problems on Canvas. So take a look at those, and I would bet that some of those are similar to these types of problems. All right. Okay. Let's go to, let's see, we hit digital. And let's do this one. So this is a logic problem. What Boolean expression directly represents the diagram above? So take 30 seconds and try that. So in class, we worked at example where we started with an expression and then worked backwards. In this case, I'd actually work forwards because we're trying to figure out what comes out of D. So let's start on the left at the inputs. So we know that this output of the OR gate is A ORed with B, or a logical addition. And then you could invert that after the inverter. So we get the inverse of the quantity A plus B. And then you could start at C and determine that the output of the inverter connected to C is the inverse of C. And so you get D equals the inverse of the quantity A plus B multiplied or ANDed with C inverse. All right. Let's put a microcontroller in the mix. So let me show you this problem. So we have a microcontroller and 3 bits out of digital ports out of the microcontroller. So bit B0 is the least significant bit all the way over here on the right. Let's see. Someone has a question. What's the difference between, let me back up to answer that question. So what's the difference between C and D on this problem? Okay. The difference is that if you invert A ORed with B as a quantity, you would not get the same truth table as inverting A and then inverting B and then ORing them together. Okay, so you could work out that truth table. If you just look at the direct implementation here, A and B are ORed together first and then inverted. If I took the inverter and I put it back here at the inputs, then D would be right if I remove this other inverter. But you could run the truth table and for that, what's in parentheses here, they would not be equivalent. Okay. Okay. Any other questions on this one? Okay. Okay. So we have a microcontroller connected to some logic. Bit 0 is this bit right here. Bit 2 is this bit right here. The rest of the bits, I'm saying, they don't matter. They could be any value, ones or zeros. You don't care, because only these rightmost 3 bits matter. And what we want to do is light up both of these LEDs. Okay, and so let's talk about this. This LED is lit up when there's current flowing through it. One side's connected to the port, the other side is connected to ground. So there's something you have to do on this side of the LED to make current flow through it. This other LED, one side of it's connected to 3 volts, and the other side over here can either be 0 volts or 3 volts because all this logic is 3 volt logic. So you got to do something at the output of this OR gate to create a logic signal here, either 3 volts or 0 volts, to turn that LED on. Okay. So these are the possible values on the right. Remember, you have all these don't care bits in here. So the left 5 bits, they don't matter. The right 3 bits matter. So which bits, which set of bits here, which byte, would make both of those LEDs light up? And I'll give you a hint. Try to write down the ones and the zeros on this diagram, or voltages if you want, 3 volts or 0 volts, to figure out how do you make both LEDs light up, and then back that up to what do the bits B0 through B2 have to be. So take a minute and figure that out. So let's work through what it takes to turn on to light up LED 1. So we have a ground on the right. That means we would need 3 volts on the left side of this LED, right? The forward current would flow this way. You would have 3 volts across this LED resistor combination to turn that LED on. All right. Let's figure out what it takes to turn the other LED on. If I have 3 volts applied on this side of the resistor, and I want the current to flow from that 3 volt source through the LED, then I actually have to make this node 0 volts, right? Because if you if you draw out, well, what's the voltage? what's the voltage across this series resistor diode pair? I would have plus on the bottom side of the resistor, minus on the top side of the diode, 3 volts. And that's the right polarity to have current flow through that LED. Okay, then we ask ourselves, well, how do we get 0 volts at the output of an OR gate? Well, there's only one way to do that, and that's to have zeros at the inputs, at both inputs to the OR gate. So the logic values are 1, 0, 0 for B0, B1, and B2, respectively. So we put them in the right positions over here. So B0 is a 1, B1 and B2 are zeros. And then the rest of the bits, we don't care. This is common in digital circuits. When you don't care about values, you just put X's. They can be whatever they want, 1s or 0s or whatever. So then you come look at your list of answers. So there's no one answer. What byte would light up both of these LEDs? Well, any byte, any 8 bits that have in the right 3 bits 0, 0, 1. It doesn't matter what the rest are. So then you have to come over here and figure out, okay, which one of these bytes, right? These are 16 bits each hex value. Which one of these bytes has 0, 0, 1 as the rightmost 3 bits? And so let's look at I'll say the nibbles, the 2 nibbles that make up the byte. Well, these 4 bits could either be a 1 or a 9, because a 1 has 0, 0, 0, 1, and a 9 has 1, 0, 0, 1. So that could be a 1 or a 9. The left hex digit, it doesn't matter what it is. It could be anything. So you come down your answers here and you look for an answer that has either a 1 or a 9 in the right digit of the hex value. And so that's going to be A. Okay? Any questions on that?
Yeah, can we clarify real quick why that can either be a 1 or a 9?
Sure. So you don't care what this is bit B3, right? That can be a 1 or a 0.
Oh, okay. I
Yeah.
think I get it now. Yeah.
So if this is 1001, then that value is a 9.
Okay.
If it's 0001, then that value is a 1.
I see. So basically, we just know that that very last digit has to be a 1 or a 9.
Yeah, we know that the rightmost hex digit over here, so the right digit in this hex value represents these right 4 bits. And
yeah, I was also wondering about the 0x notation. Somebody just asked that in the.
Oh yeah. Oh, okay. 0x notation. Yeah. So you'll see this in your book too, and you'll see this in programming languages. Yeah, I should have pointed that out here. 0x when you're programming like an Arduino or anything, or just writing down a hex value. 0x is a notation for X. It's different. I should have pointed this out. It's different than this don't care notation. 0x means base 16. Another way of writing that is F9 followed by a subscript of 16.
Okay, so if we just 0x just denotes we're looking at a hexadecimal number.
That's right. That's right. It's when you're programming in C, it doesn't recognize the subscript, so you put 0x. Yeah. Yeah. Thanks for pointing that out.
Thank you.
Professor, what is binary with that kind of notation? Is it?
Yeah, some compilers use 0B. The IAR compiler and it would use 0B. There might be something different for the Arduino compiler. I don't know what that is. But when I write in this class, if I write binary, I'll put the subscript 2 because 0x is pretty universal for hex. Binary changes between compilers, so I'll write a subscript 2 if it's binary.
Thank you.
You're welcome. Okay, other questions on this? All right, let's bring a transistor into the mix. So let's suppose X and Y are 5-volt logic signals. Let's suppose this resistor here, which is unlabeled, is designed such that the transistor is either saturated or in cutoff, depending upon the value of X. So X and Y are 5-volt logic signals. The logic level 1 means the voltage is greater than 4 volts. Logic level 0 means the voltage is less than 0.3. So you can assume that when X is equal to 1 or greater than 4 volts, that the transistor is saturated, and when X is equal to 0, the transistor is in cutoff. Okay, so then if X is a logic 1, then what is the logical value of Y? So take 30 seconds and try that. So let's make X a logical value of 1 by setting it to 5 volts. So if X is 5 volts, then you have current flowing into the base. It's going to be greater than 0, and we know that the transistor is saturated. And that means saturation voltage, it's about 2.2 volts or less. So VCE here is equal to the node voltage VY, right? And that would be a logical 0. So this is actually a logical inverter. Apply 5 volts at X, you get 0 volts-ish at Y. Apply 0 volts at X, you get about 5 volts at Y. Okay. Okay, and then, well, take 10 seconds and figure out if X is logic 0, what happens here? If X is 0, then what are the currents and the voltages, and then what is Y? So if I set X to 0, that means I have no base current. Right? I have 0 here at X and 0 here at ground. There's no current flowing into the base. That means there's 0 current flowing through that collector resistor, which means there's 0 volts across that collector resistor. And a KVL would show VCE is 5 volts. So Y is 5 volts. So the answer is 1. All right, let's throw a motor into the mix. And so you have a motor that you want to cause to spin. So what hex value do you have to use for B0, B1, B2? Combine that into a single hex digit. What hex value would cause the motor to spin? So you're going to program a hex value into this set of bits in the microcontroller. And they're organized like this in the lower right. So take 30 seconds and try that. So let's figure out what we need to make that motor spin. I need to have base current into that transistor in order to have collector current flow so that motor spins. And so that means I need a 1 over here, or let's say it's either 3 volts or 5 volts, depending upon the logic. To get a 1 out of an AND gate, that's an AND gate, I need both inputs equal to 1. So now going down both of these logic branches, I got to figure out how do I get a 1? Well, to get a 1 at this top branch, well, let's go back to behind the inverter. I need a 0 behind the inverter. And that means into an OR gate, to get a 0 at its output, I need 2 zeros. Going down the other branch, to get a 1 out of an OR gate, when one of its inputs is connected to 0, I need a 1 at the input, at the other input to that OR gate. So I organize these in a word down here. I have a 3-bit word, and to represent that in hex, that would be a hex 4. Okay, questions on that? So it's, let's see, it's 6:30 now. I'm going to continue on with some of these review problems. I'm also going to post this video. I'm going to try to get it up tonight if YouTube is cooperating with me. So you're welcome to stay. We'll consider this office hours now, or if you want to drop off, you're welcome to, and you can watch the video later. But I'll just keep going here. So there's a motor in the mix there. Let's talk a little bit more about motors. What technique is generally used to control the speed of a DC motor? Which one of these? So take 15 seconds and figure that out. So we talked about 2 techniques to apply to a motor, and the 2 listed here, H-bridge and pulse width modulation, we talked about. So the way to control speed with a motor is pulse width modulation. You vary the duty cycle of the pulses in order to control the average power delivered to the motor, and that's how you control its speed. Okay, how about direction? Take 15 seconds. How do you control direction of a DC motor with, well, which technique do you use to control direction? Okay. Well, the other option we talked about, the other technique we talked about was the H-bridge. So the H-bridge controls the direction of current through a DC motor, and that allows you to control the direction it's spinning. So let's dig into this H-bridge a little bit. Here's a diagram of a motor and an H-bridge. Which switches need to be closed to cause the DC motor to spin in the forward direction? Switches are labeled 1 through 4. So take, I don't know, 15 seconds and figure that out. So we want current flowing from left to right through this motor. Current's trying to flow, if it were given a path, from the 5-volt node voltage up here to ground. And so we want current to flow in this direction. So we'd have to close switches 1 and 4. All right. Continuing on with the H-bridge, we talked a little bit briefly about NPN and PNP transistors. So what digital word would cause the motor to spin forward? Where a logical 0 is 0 volts, a logical 1 is 5 volts. You can apply those logical signals through two WXYZ terminals. And so remember, how do you get base current to flow through this NPN? And then how do you get base current to flow through this PNP transistor? And then fill those values in over here. So take 30 seconds and figure that out. So we can draw the current the way we want the current to flow through the circuit. So it's down this way from the source, left to right through the motor, and then down to ground. So we have to saturate transistors W and Z, and then leave the other two in cutoff. So in order to saturate W, I have to cause current to flow emitter to base, right? Current goes the other direction for a PNP transistor. So if I have 0 volts here and 5 volts here, that will cause current to flow through this diode junction, emitter to base. For the X transistor, I want that turned off so that it's in cutoff, and all I have to do there is apply 0 so that there's 0 on the base side of the transistor. There's 0 volts on the emitter side, so there's no current flowing into the base. If you go up to Y, I want this transistor in cutoff. So the way to have 0 volts across this base to emitter junction is actually to apply 5 volts at Y. So if I have 5 volts at Y and 5 volts here at the emitter, there's 0 volts across that junction, so that transistor will be in cutoff. And then at Z, I want Z on. I want Z saturated, that transistor saturated. So if I apply 5 volts to the right of the base resistor, and I have 0 volts at the emitter, current will flow, that transistor will saturate. So I organize those bits in a word as indicated here, and I get the hex digit C. Okay, let's do a motor related problem. Okay, Vx is a pulse width modulated voltage. What duty cycle of Vx will produce an average voltage of 3 volts? So you want, another way to think of this is, what duty cycle do you need to have the average over one period be 3 volts in order, let's say, to drive a motor at a certain speed? So take 30 seconds. Okay, so the duty cycle is the time that the voltage is high over the period. So you could write out an integral, or you can observe that when you have only 2 levels of voltages, that you could actually kind of eyeball the integral. Well, you can calculate the integral, the area under that curve, by multiplying 2 numbers, 12 times the time period to integrate. So the average voltage is actually the peak voltage times the duty cycle. And if you want the average voltage to be 3 volts and the peak is 12 volts, then you can calculate your duty cycle, 25%. Okay? Questions on that? So that's those are the example problems that I wanted to present in class today. There are more problems on Canvas, and as you can tell, I would definitely study op amps, because those are useful electronic circuits. If you need to build an amplifier in the future for a product, probably going to use an op amp. If you need to compare 2 voltages, it's probably going to be an op amp or an Arduino, which is why we cover also microcontroller topics. So what I'm going to do now is end here, and let's see here. What I'll do is I'll stop for a couple minutes, and if you want to stick around for office hours, then definitely do so. And if you want to just ask questions or listen to questions, you're welcome to do so. And if you're still on. Thanks for taking the class. I think this is the last time we're going to get to talk, except for office hours, unless you stick around for office hours. So thanks for taking this class. I really hope the topics are useful. I really think that when you encounter circuits like this in the future, that you're going to be able to reach back and remember what an op amp does, or at least you'll be able to go find what it does and refresh your memory. I think that when you encounter something that needs to be controlled, you'll remember a microcontroller. You'll know that you can sense values with an analog to digital converter. You can sense digital values. You can output values. And I think that will be useful for the future. And you'll be able to talk to electrical engineers and other engineers at a systems level to be able to work on bigger systems. And so what I'll do now is I'm going to drop off for 2 minutes, and I will be back to start office hours. So see you in a couple minutes if you want to stick around.